Hello, everyone. Today we're going to be talking about properties of gases and also pressure. The properties portion is short, which is why I'm going to go through two sections today instead of one. So, as we talked about in the previous section, gases don't have any molecular forces, or we're assuming that they don't exist. Okay, if you compare gases to solids and liquids, solids have very strong bonds. Liquids don't have as strong of a bonds, but they have strong intermolecular forces to keep things together. And gases are so far apart that we assume that there are no intermolecular forces in the gases. Okay, that's just a refresher from yesterday, and that's one of the properties of gases. That's something that we assume all gases have. Okay, and they also expand to fill their containers. Okay, if you make a container larger and there's a gas in it, the gas is going to expand to fill the whole container. Okay, that's a property of gas that all gases follow and do. Okay, because of that expansion, we assume, well, it's not an assumption, it's a fact. Because of that expansion, gases tend to have very low densities. Okay, the molecules are super far apart. Because of that, their densities tend to be super tiny, as you can see. Okay, so let's say we had some ice. Okay, if you were, that ice has this density 0.91. If you were to melt that ice, the density would then become 0.98. And then if you were to boil that water and make it vapor, it drops drastically to this. Okay, so gases have very, very, very low densities. Okay, that's a property of gases. That's gases all across the board. Okay, but it's because of that low density that we can use, or we can manipulate it in certain ways. Okay, because it's super, super low density, we can compress it very easily. Okay, and that happens in engines and many different other things. Okay, gases can be compressed. Okay, they can be compressed. Okay, so those are the three major things, or the four major things. They don't have intermolecular forces. They expand to fill their containers. And they have very low densities, and they're compressible. Okay, those are the four properties of gases that all gases have. Okay, they all have that. Okay, we're gonna skip these questions because they do not that they're not relevant, but they're not important for the major points that I want to get across. Okay, now we're gonna get into pressure, more specifically how we measure pressure, some of the tools that are used to measure pressure. Okay, in order for us to completely understand what a gas is going to do, we need to know the pressure of it. We need to know the volume of it. We need to know the temperature of it. And we need to know how many moles we have, or how many particles. Those four things are what is going to dictate how the gas overall is going to behave. Okay, but for now, we're going to focus on pressure. Okay, what is pressure? Pressure is simply how much force you put on something over a specific area. Okay, pressure is force per area, and the unit of it, or the SI unit of it in chemistry, is Pascal. Okay, Pascal. The units that we use to measure it, force is going to be in newtons. Okay, newtons is the unit of force. Okay, when you guys end up taking physics, you're going to see this a lot. And then area, we want it to be in meters, meters squared. Okay, meters squared is what the units are going to be. Okay, and then if you take newtons, newtons divided by meters squared gives you a Pascal. Okay, so 1 Newton per meter squared is the same thing as 1 Pascal. Okay, so that's what a Pascal is. There are other units of pressure that is used probably more frequently, and that is atmospheres, or ATM. We'll get to that in a second. Continuing with the trend of just understanding what pressure is again force per area. Okay, so in the case of objects, how much force do objects put on other things? Well, since they're not in motion, the force that they put on things just has to do with their weight. Weight is a force. Weight is the force of gravity pulling down on you, right? So let's say we have a book, okay? We have a chemistry book. If you lay the chemistry book out flat, you have less pressure. Why do you have less pressure? Because think of the force is staying the same. The force is the weight of the book. So the F it's a number. But the area in this case is large because we laid it down flat. So you have the whole surface of the book being spread out on the table. But if you were to stand the book up and put it on its edge like this, okay? If you were to stand the book up like this, now you have more pressure. Why? The force remained the same. The force is just the weight of the book. But now we made the area smaller, okay? We made the area smaller. So that increased the P, because if you make the denominator smaller, you're going to get a bigger number, okay? So the way you place objects, that determines how much pressure you're going to get, okay? That makes a big deal. There's a reason knives are so efficient, okay? Knives have a pointy edge. That edge is super, super tiny, okay? The end of a knife is just one point, okay? That's important because it means the area is super, super tiny, which means with just a little bit of force, you can get a lot of pressure, okay? That's some of the science behind the knife. That's why they get those pointy edges, okay? It's to make the area small, which allows you to get a lot of pressure for a little bit of force, okay? So that's what pressure is. It's just force per area, all right? So now let's think about our world, okay? On planet Earth, the normal pressure of you just walking around, on the surface of the Earth, the pressure that we experience is 1 atmosphere, 1 atm. Or, since we talked about pascals being our SI unit, it is 101,000 pascals, okay? That is the pressure that you feel just walking around, just existing, okay? That's at the surface. Yeah, it's at the surface of the Earth. That's the pressure that we feel. How do we know that? We have some tools to measure that we came up with, okay? Now we're going to talk about some of the instruments that we use to measure, okay? The barometer is one tool that we use to measure pressure. How does it work? Well, you have a tube, okay, and you have a pool of liquid. The air pressure is force per area. The air is pushing down on the liquid. And since the liquid has nowhere else to go, it goes up in the tube, okay? So that's how we figure out what the pressure is. So the air is pushing down evenly on all sides. It's pushing down everywhere, okay? And if it's pushing down everywhere, the liquid has nowhere else to go but up this tube, okay? So the height of this tube, it's what's going to provide us with the information for the pressure. Okay, that's all a barometer is. You may or may not have heard that term before, but that's how we measure pressure, with a barometer. Okay, we look at how much force or how high up this liquid goes in the tube, and we use that to calculate pressure. And there's the equation should be here somewhere. Okay, it's probably a little further down. But what you do is you take the density of the liquid, you multiply that by gravity, and you multiply that by the height, and that'll give you a pressure, okay? So let's think about this. We have an example here just so we can practice reading this. You have pressure pushing down on the mercury, and it goes up a certain height, okay? This one comes down here, this one's here, okay? Which one has the higher pressure? This one has the higher pressure because the liquid goes up higher, which means you have to be pushing down on this thing more, okay? Think about it like that, do they have them at circuses? Those things where you get the hammer and you smack it and that launches the bell up, okay? The higher the bell goes up, the harder you hit it. This is exactly that. The harder the air is pushing down on the mercury, the higher up it goes, okay? And that's how you measure pressure with a barometer. That's how barometers work, okay? So that's the idea behind that, okay? Here's the equation here. So pressure is equal to density times G times the height of the column, okay? So if you're designing different barometers, you don't have to use mercury, but the reason they use mercury is because mercury has a very high density, and the high density allows us to have a smaller h, okay? So let's say the pressure is a certain number, it's always the same number. At the surface, P is always the same number, okay? So we can adjust the density and the height of the column. Gravity always remains the same. You can't change G. So if you want to design something that's small, you can adjust the density and you can adjust the height, okay? So if we have a low density, that means we need a tall column to get the same pressure, okay? If you have a high density, that means you can make it smaller, okay? So that's what this is. If you look, if we replace the mercury with the water, the density of the mercury is basically 14 times greater. And if you look at the height, with the mercury, it goes up 2.5 feet. With the water, we would need 34 feet. So you would need a very, very tall column just to measure the pressure. And that's not really feasible or desired. You know, that what's the point of a tool that's freaking that huge? Okay, it's pointless. So that's how barometers work. Pressure down in the liquid goes up. How high it goes tells us that, okay? So you're going to see this term a lot. So 1 atmosphere, okay? 1 atmosphere so far. Well, let me, do I have, where, okay, I need a blank spot. Okay, let's do it here. So 1 atmosphere is the pressure at the surface, okay? 1 atm. That is the same as 101,000 pascals. And you're gonna see one more unit, and it's gonna be weird because it's in height, but you'll understand it in a second. 760. This is millimeters. Millimeters of mercury. Okay. So this goes back to the barometer. Barometers use mercury, and we just said we use mercury because mercury has a high density, so it doesn't have to be that tall. Okay. So at the surface, when you have 1 atmosphere pushing down on this thing goes up 760 millimeters, okay? So that's why we use millimeters of mercury as a unit of pressure. And if you continue studying science and chemistry, you're going to see that a lot. Millimeters of mercury, I think that's what they use on the weather channels and things like that. They use millimeters of mercury when they're measuring, when they're giving you the pressures and things like that. Pretty sure that's what they use. Okay, but this is what they're referring to. They're referring to how tall this thing goes up in the column. So 760 millimeters is the same as 1 atmosphere. Okay, so I just wanted to let that be known because you're going to see that a lot. Okay, you're going to see that a lot. So that's enough with that barometer. There should be another one. Okay, they also use it in airplanes. So there's different types of barometers, but in an airplane, they need to know what the air pressure is. So they have those built into planes, okay? Continuing with standard pressure. This is exactly what I just, ignore the bar. Don't worry about bar. We'll worry about bar another day. But bar is another unit of pressure. Just know that, okay? If you want to look, these are all the different conversions, okay? And here we go. This is the last tool, okay? I'm skipping these questions. I'm not worried about these questions. Manometer, okay? Manometer is a little different. A manometer is used to measure the pressure of something, a gas, okay? So that's what a manometer is for. So if we want to figure out how much pressure this gas is exerting, we use this. So a barometer is used to measure the pressure around us, so on the surface. A manometer is a tool used to measure the pressure of something specific, something that we want to measure, a gas that we want to measure, okay? That's how we measure the pressure of that. It's a manometer. How it works is this. So you fill up this container with gas, right? Pretend this is closed. This valve here is closed, okay? We fill up this container with gas, okay? Boom. Then what we do is we put mercury inside the tube. Okay, boom, that's set. Then after that, what we do is we open up the valve and we see how high the mercury goes. That will tell us the pressure inside of here, okay, which is what we're looking for. Okay, that's how that works. So originally, when you first put the mercury in, the mercury is going to be at the same height. Okay, if you ever filled up something with this type of shape, you're going to see that if there's no pressure, the liquid, it's going to level out on both sides. But as soon as this opens up, this pushes down here. Okay, this pushes down here and it makes the liquid go down. And so it ends up getting taller on this side and shorter on this side. That difference, notice they're measuring the difference in height between these two things. That difference in height is what's going to tell you what the pressure inside of the container is. Okay, so that's how a manometer works. Okay, that's how that works. Okay, so what you do is you take the pressure outside, because we know what the pressure outside is. Okay, the pressure around us, whatever, we know what that pressure is. And then you add the pressure from the inside of the tube, and that'll tell you what the pressure inside of here is. Okay, so in equation form, it's this. The pressure of the gas inside the tube or inside the container is equal to the pressure outside. Okay, PATM is atmospheric pressure, the pressure on the outside, plus the pressure that you get from here. Okay, and so that's how you figure out what the pressure is. Okay, and that's how that works. Okay, and then, yeah, I think that's it for today. Okay, so quick recap. The four characteristics are gases: no intermolecular forces, they expand to fill their containers, they have very low densities, and they're compressible. Okay, and then you have two tools to measure pressure. You have a barometer. The barometer measures pressure by height. Okay, the harder you push down on it, the higher it goes. Kind of like that that toy at circuses or carnivals that you smack the thing and the bell goes up. Okay, kind of like that. And then you have a manometer. Okay, a manometer is used to measure the pressure of a specific gas. Okay, barometers for outside, manometer is for specific gases inside a container. Okay, that's the summary for today. How are we doing on time? Okay, we are at 18 minutes. Not bad. So for today, you have another multiple choice. Okay, it's going to cover the properties and the tools. Okay, so these 1, 2, and 3 are conceptual. So I will leave you to that. In terms of mathematics, 4 is a math problem, 5 is a conversion, 6 is conceptual, 7 requires some math, and the other ones are conversion. So the only ones that really require any calculations are number 4 and number 7. Okay, so let's look at them. Number 4 is saying a gas at a pressure of this exerts a force of blank. Okay, for that you need this equation. The pressure is equal to force divided by area. Okay, pressure is equal to force divided by area. You are looking for force, which means you need to move area over. Okay, so then you get F is equal to P A. Okay, that's what you need for that one. And then I'll leave that up to you. For number 7, that's the equation for the barometer. Pressure is equal to gravity times height times the density. Okay, what you need to calculate is this new height. Okay, so G is the same no matter what. You know how tall it is with the mercury. What you want to know is how tall it's going to be when you replace the mercury with the water. Okay, so the only thing you're adjusting is the substance. Okay, you see how much greater the density is for mercury than it is for water. You can use that ratio to figure this out right away without doing any major math. Okay, you can figure that out right away without doing any major complicated math. So instead of having to rearrange any equations, I will give you a hint, wink, wink. The difference between these is what you're going to multiply by to get that height, okay? So how much greater is mercury, the density is in water? Use that number and multiply it by the 713 to get your new height, okay? That's how you do the math for number 7. The rest of them are conceptual and just require you to think a little bit, okay? But that's it for today. I hope you guys are doing well. Okay, take care, be safe, and enjoy the rest of your Tuesday.